In this video, we will be answering a few questions. Actually, not a few. A little more than a few questions on partial derivatives. So previously, the lesson was about transcendental curve sketching. So you look for 6 things in every question. Diaspora. So this time, the lesson that comes after it is called partial derivatives. So let's start. So what are partial derivatives? How is it different from the usual way of differentiation? So given, so this is something that you have to know. Partial derivative of z with respect to x. So how do you write that in, well, a mathematical notation? So you write it as this. So with respect to x, the x is at the denominator, and the partial derivative of that variable is going to be in the numerator. And when we say partial, so this is the symbol that you will always be writing. Another way of writing this notation is this. So in the denominator, it's still the same. In the numerator, we write partial derivative of x of xy. So essentially all elements. Another way is this. So we basically just placed f here, and the elements are already self-explanatory. That's why it is written that way. Another way is this. So you write it. That's the only difference, really. Partial derivative z. Okay, so another way of writing this is this. Let me list down the other notations. Although essentially this is the most commonly used, so best you study this only. Although it does help if you are familiar with the other notations, what I'm writing, because there is a good chance, although I haven't proven it from my experience, I was expecting that because we were introduced to these notations, let's say there is a question regarding partial derivatives, we were asked to find the answer to a certain this, but then it was written in a specific notation. So instead of what's given is this one's provided instead. So fortunately, from my experience, I didn't see any of that in the finals. So either in the quiz, basically the assessment right after the lecture. So, but yes, you never know. So yeah, those are the notations when you say this specific phrase, partial derivative of z with respect to x. So let's answer a practice question already. So z is equal to x squared y minus e raised to x plus 6y squared. So that is our equation. We have to determine partial z over partial x. Also, we have to determine partial z over partial y. So, what do we do? So, it is clear that in the equation we have 3 variables, x, y, z. E isn't considered. That's Euler's number. It's technically a constant. So, specifically for dz over dx, partial z over partial x, usually this is just, I'm not confident although I'm not saying that I'm certain, I'm not confident to call this derivative, rather partial. That's the more fitting word. So, okay, going back. Since we have z and x in the fraction, we will render whatever the variable isn't in this fraction as a constant. So apparently we have three variables, right? And what's not here is y. Therefore, we regard y as the constant. So then we derive. So x squared y, I believe we have to... No. We're not going to do product rule. Again, y is a constant, so don't be confused. So what do you do? If there's a constant, you set it aside, right? At the left side. And then you apply power rule. So bring down 2, x, and then n minus 1. That's going to be 1. Derivative of e raised to x, just the same thing. And apparently this y is a constant, right? And everything else is a constant. So that's going to be 0. So that's basically it. 2xy minus e raised to x. That's the answer. Also, one thing that I have to tell you is that for this, although y is a constant, usually, right, the idea is the derivative of a constant is 0. However, as long as it's multiplied with a variable, you just technically they're still multiplied to each other. It isn't on its own, so you cannot say that the constant is going to be 0. It is still technically morphed together with the variable, so that's why we have 2xy. Okay, how about partial z over partial y? So this time we render x as constant. So since x is a constant, x squared, put that aside, derivative of y is 1. E raised to x, x is a constant, right? So e raised to 1, that's, well, it's a constant, so 0. And then power rule, 12y. X squared plus 12y, so that's the answer. Okay, so it's essentially an extension of your skill set in differentiation. Usually partial differentiation involves more than 2 variables, but I think that applies in all cases. At least 3 variables according to my schema, although don't trust it. For a function f of x, y, z, so let me just show you a picture of my notes. I don't have to write everything. So for a function w is equal to f of x, y, z, so when we say partial derivative of y with respect to x, we can write that as partial w over partial x. So same logic as the one earlier. So other notations are these. How about partial derivative of w with respect to y? So apply the same logic. Those are the notations. And partial derivative of w with respect to z. So again, same logic. Also, if you noticed, we have d1, d2, and d3. Why is that? So according to the order, x is at the first position, y is at the second, z is at the third position. So the positioning matters in that sense. How about this? So given we have f of v, w, x, y, z, what is d4? So the fourth variable, 1, 2, 3, 4. So partial f over partial y. Y is the fourth variable. Okay, so that's basically it. Okay. So essentially, partial derivatives in the aspect of geometry, although you don't have to really know it, uh, it helps visualize, I guess. So it basically manifests as a plane. Let me show you. So, yeah, I'm not gonna explain that anymore. I don't remember. Let's have another practice question. That's what matters more. W is equal to x cubed arc sine y squared over z raised to 4. So we have to look for partial w over partial x, partial w over partial y, partial w over partial z. Okay, so first let's look for partial w over partial x. So apparently we have 3 variables, x, y, z, again. And so we have w and x over there. So the remaining variables we regard as constants. So that's going to be y and z. So let's differentiate in consideration to that. So 3x, we're going to apply product rule. So arc sine, just copy. So arc sine, you have to remember this again. d dx sine arc sine u. So that's going to be equal to 1 over 1 square root of 1 minus u squared times du over dx. Or essentially just u prime. So how do you apply that? Let's try just 1 over square root of 1 minus u is this. So y squared over z raised to 4. And then du over dx. Essentially, since y and z are constants, the derivative of u is going to be 0. So yeah, everything here is 0. So what do we have left? So this is the final answer. Okay, next. Partial w over partial y. So x and z are constants. Okay, so we're gonna do product rule again. X cube, that will be 0. And then x, just copy, arc sine okay, so we apply quotient rule for the derivative of u. Denominator, copy, times derivative of the numerator minus y squared over, so z is a constant, right? So 0. Below, z raised to 4 squared. So let's see, 2x cubed let me check. Okay, so 2x cubed y z raised to 4 divided by z raised to 8 square root of 1 minus y squared over z raised to 4 squared. We can cancel something. So 2x cubed y over z raised to 4, then just copy whatever is in the radical. Okay, that's it. Or side quest, you can simplify this already. Distribute the exponent. Although personally, I don't think that's necessary at that point. But in some cases, I think you have to simplify if can be. Okay, partial w over partial z. So this time we consider y and x as constants. So product rule again. X cubed is still going to be 0. Then copy plus x cubed times 1 over square root of 1 minus y squared over z raised to 4 raised to 2 times z raised to 4 derivative of y is 0. Y squared over 4z raised to 3 over z raised to 4 raised to 2. Okay, so you have x cubed minus no negative x cubed 4z raised to 3 y raised to 2. We'll arrange that later. Z raised to 8 over square root of 1 minus y raised to 2 z raised to 4 raised to 2. We can cancel something, z variable. So we have negative 4 x cubed y squared over z raised to 5 and then square root of, you get the rest. I believe we can simplify something further here. Yeah, we do. So if you simplify further, this is what you'll get. LCD at the square root. Okay. So since the radical is raised to 2, right? So apparently when we liberate this one to the other side, we'll have z raised to 5 over z raised to 4. And then what we have left in the radical sign is z raised to 8 minus y raised to 4. This can be simplified as just z. That's it. Okay, we're done with this. How many sample problems can we answer? Ooh. I low-key wanna take on the spiciest questions already. Although, coming from the end of the audience, who might not be a master of this topic yet. I'm not saying I'm a master. It just so happened that at one point, I was able to solve something that isn't that easy. So, I consider that an achievement. Let's see. Okay, let's try this. Z is equal to y squared over y plus, x squared over y plus y squared over x. Look for partial z over partial x. Also, look for partial z over partial y. So, for partial z over partial x, we will render, okay, let's see how many variables we have, x and y only. So, in that case, y will be a constant. So, we apply quotient rule since we have fractions, right? Since y is a constant, so copy derivative minus copy and then derivative of y is 0. Copy derivative minus copy wait, this is supposed to be 0 since again y is a constant. You don't apply power rule. A constant's derivative is 0. Derivative of x is 1 over x squared. So simplify. Minus. Okay, that's it. Actually, we can simplify further. Cancel. 2x over y minus y squared over x squared. That's it. How about partial z over partial y? So, I just noticed it's kind of hard to solve partial derivatives on iPad. Especially if your screen isn't that big. Okay, so y is going to be a constant here. Again, quotient rule. So copy y, derivative of x, minus copy x squared, and then derivative of y is 1 over y squared. Copy derivative, copy derivative over x squared. Negative x squared over y squared plus 2xy over x squared. This can be 2y over x. That's it. That's the final answer. Let's try another question. Another set. So we have z is equal to a raised to x squared plus xy. We are to look for partial z over partial x. Also look for partial z over partial y. So what do? We're gonna base our solution on this formula. Usually in the case of just e raised to x, it's equal to e raised to x times the derivative of x, which is 1. So it doesn't make any difference. So in this case, we just copy the entire thing. And then du over dx is going to be the derivative of all the terms in the exponential position. So let's try brackets. By the way, y is going to be a constant, just to clarify. So x squared becomes 2x because of power rule. Xy, y is rendered as a constant, right? So x is going to be 1, and then just copy y, plus x times y is a constant is 0. E raised to x squared plus xy times 2x plus y. That's it. That is the answer. Okay, so here we render x as a constant. So derivative of x squared is 0. Quotient rule. So derivative of x again is 0. Copy y plus copy x. Derivative of y is 1. Simplify. That is the answer. Okay. So far, I hope you share the same sentiment. Partial derivatives is fun. I feel that it is compared to the other topics under differential calculus. You just have to know the rules and you'll do fine. Even if the practice question becomes more complex, as long as you abide to the rules, you should be fine. Or at least you should reduce the chances of messing up somewhere at one point. Let's try something that involves trigonometry. Let's make it spicy. So given x cubed z plus xyz is equal to 16 sine xy minus y squared. So we are only tasked to find one thing. Derivative of, partial z over partial x. Okay, go. So first thing, y is known to be the constant here. So partial z over partial x is equal to, wait. Okay. This is an example of implicit partial differentiation. So in differential calculus, what has already been taught to you is supposedly is implicit differentiation. So that comes somewhere after just classic differentiation. In partial, what we've been doing so far was the classic way, just partial. This one involves elements that we study from implicit. So implicit partial differentiation. What's the difference essentially? So we have this. I mean, personally, that's from a personal level, that's actually just the only difference, and that already tells us that there are certain rules that we follow. So it's definitely not the same as what we've been doing. And how do we exactly do that? So we don't write this anymore in our solution. We already know that y is a constant. We just differentiate, similar to implicit differentiation. So product rule for x cubed z. 3x times z plus x cubed times 1 plus... Ooh. Okay, so in product rule, what we usually do is just solve when two variables are involved. But since we have x, y, z, don't be fooled, because again, y is a constant, so actually we just have two variables. X is gonna be 1, z plus x times 1 equal to y is a constant, right? Let me just cite this. So derivative of sine u is equal to cosine u du over dx. How do we apply that here? So cosine xy times the derivative of xy. So that times y is a constant, right? So 0. And then again, y is a constant, so y squared is just 0. Okay, so that's it. What have I been missing? Oh yeah, one very important detail that you have to know when solving implicit partial differentiation, sorry, implicit partial differentiation problems is that so we write partial z over partial x. Where do we write that? So let's go back here at x cubed z. So we have a z variable, right? Its derivative is 1. But along with it, beside it, we write partial z over partial x. Does it sound familiar? It's supposed to, if you've already been through the classic way of implicit differentiation. So you have something like this. Also, here, derivative of z. So it's here, right? Aside from 1, you also write partial z over partial x. At the right side of the equation, there is no z. We didn't differentiate anything. So yeah, this is important because it will dictate what we have to find. Actually, that is what we have to find. The rest of the other terms, variables, have to be moved to the right side. These have to be at the left side. So let's simplify, make it easier for the next step so we can segregate yz. Oh, okay. 16y. That's it. Anything to transpose? So transpose 3xz, also yz. Factor. And then just copy this. And then divide both sides by this. Oops. Therefore, you get this as the answer. So, yeah, that's how you solve implicit partial differentiation. Any other sample problems? Okay, let's try this one more problem. X cubed plus y squared minus z raised to 4 plus 3xyz equal to 5. Partial z over partial x, partial y over partial z, partial x over partial y. So these are what you have to find. How do we start? How do we start? Let's try to solve first for partial z over partial x. What kinds of variables do we have in this equation? X, y, z. Okay, 3 variables. So we only have one variable. That's a constant. That's going to be y for this notation. So 3x plus 0 minus 4z cubed plus, set aside the constant, so that will be 3y. Product rule for xz. x1, z, x1. The constant in the right side of the equation will be 0 because it's a constant, clearly. At that point, just put this. It's not part of the equation. 3x minus 4z cubed plus 3y z plus 3xy equal to 0. Wait a minute, I forgot to do something again. So you put this whenever you find the derivative of z, right? So here in z raised to 4, it's this one. So after deriving d over dx, dz over partial z over partial x. Where else? Here. Okay. You will feel that you're missing something when you couldn't determine what's the next step. The next step involves this. What I didn't write just yet. So I meant a while ago. 3xy partial z over partial x. Okay, let's start transposing. 3xy minus 4z. I believe we can merge them like that. Negative 3x, negative yz. Partial z over partial x is equal to, well, this is going to be the numerator. This one will be the denominator. Okay. That's it. This is the answer. Okay. Let's find partial y over partial z. Let's just put this aside for now. We need to really read the equation. So solving in another space with this being not visible is just hard. So x is going to be a constant. So 0 plus 2y minus 4z. By the way, since this is partial y over partial z, y is in the numerator. Whenever you find the derivative of y, you write exactly this beside it. So it's applicable here. You write it like this. Minus 4z cubed plus 3x, and then product rule 1 times z plus y times 1 equal to 0. Don't forget. Two y partial y over partial z minus 4z cubed plus 3xz Okay, oops, just copy this, and then this one will be in the denominator. Let me check. Are we good? 2y dy over dz, 4z cubed 3zx. Wait a minute. Oh, wait. Give me a few minutes, maybe just seconds. We'll see. 3xy partial y over partial z. Oh, this was supposed to be here. My bad. That's it. That's the right answer. Now, partial x over partial y. That's what we have to find. Z is going to be the constant. X cubed 3x squared plus 2y minus 4z. Don't forget partial z, partial x. So partial x over partial y over here because of the x over there. Don't even bother using power rule. Z is a constant, right? So 0. 3z xy, product rule of xy. 1 times y, partial x over partial y times y plus what? Copy x and then derivative of y equals to 0. Okay, continue. Three yz partial z over partial y is equal to negative 2y minus 3xz. I think we're good. Yep. Okay, our answer is correct. So, we're done. Let me see if there are more problems that I'd like to solve. Like what my professor said, technique is repeated practice and determining which variables be held constant. I wrote this quote in my reviewer. I think that would be it for this video. The next one is technically still partial derivatives, partial differentiation rather, although there's not much of a difference. Higher order derivatives and partial differentiation at the same time. Okay, so that will be the next lesson. And what comes after that is total differential. So essentially, this is another way. I spoke about this videos back. This could be applied in for when you want to find what's the context again? A box. So the scenario is a box with various dimensions. So same base and height. No, rather same length and width, but the height is different. We want to approximate the box's volume, but then we have what do you call this? Errors in terms of increments. So, for example, the radius of a sphere is 36, but the actual radius was 35. So, that affects the volume as well. So, that kind of sort. More on the applications of total differentials in the next video. So, yeah, that's it. Thanks for watching.